Good evening, everyone. In the previous class, we have seen what is a tree and different definitions, terminologies to understand about trees. We have seen different types of traversals, that is, visiting through all nodes of the tree, like in order, pre order, and post order traversals of a tree. Now we have to write programs for implementation of binary tree. So one of the main types that we have seen yesterday is a binary tree. I told you we can have any number of child nodes, but specifically or standard nodes that we can use is binary tree. We have something called as B trees. In B trees we can have more than two child nodes also. We have B plus trees wherein we might have one more additional child node. So there are various types which we will be going through one after the other. But most important thing when it comes to implementation is binary trees, and if you have very large records they will use B plus trees. So these are the two standard ways of implementing, two standard types for implementing tree data structure. Now we have there are different considerations here that you need to look into. Say for example, what you have learnt in stacks, queues, list and all, we had just a list of elements. So if I have to insert elements, then I'll just give a list. In the order in which I'm going to give, the elements are going to be inserted. How it is retrieved or processed depends on whether it is a normal list or stack or queue. Whereas insertion, for everything there was a procedure, right? In case of stack, the insertion was allowed only at one end, deletion was allowed at the same end only. In case of queue, insertion was allowed at one end and deletion was allowed at the other end. And in case of normal linked list, we had written all possibilities like various insertion options and various delete options, everything were considered. So that was in linear data structure. Now in a tree data structure, there are certain things that you need to consider if you have to insert a binary tree. You have to construct a binary tree. When you construct a binary tree, it means you have to give certain elements, right? A, B, C, D, E. So like this you have to give some elements. Suppose these are the elements that you are giving for insertion. Now how does it get inserted? Will it get inserted as A as the first node, then B here, then C here? Will it get inserted this way? D and E, say F and H. We have written different examples in yesterday's class wherein there is a possibility that this node is not there, isn't it? And this additional G, it can be left child of D or right child of G, can be anything, isn't it? So there is no specific format for, or I can write it here, or I could have written here. So there is no specific format. And what is the guarantee that it is a proper binary tree? Both has left child and right child. What is it? What if it has like this? So this is B. There is no right child at all. You can have C here and D here, isn't it? And then you can put E here, F and H. So there has to be an order in which we write. Therefore, when we give elements, how to construct binary tree becomes very difficult if I don't have further types. So in binary tree, we still have further types. Based on the types only, we can create a tree. And in the previous class, in yesterday's class, we wrote post-order traversal, or we constructed a binary tree based on in-order and pre-order traversals, right? That was a theory-based question. It cannot be a program-based question. That is, I gave in order and pre-order, and we wrote tree for that. We constructed tree for that. And I gave in order and post order traversals, and we constructed tree. So that is to just as a theory question in your exams. It won't be practical implementation, or in other words, think about real life situation where you are creating applications. You cannot give a software in order pre-order traversals and expect it to construct a tree. It is like tree is existing. For that tree you have written in order and pre-order traversal. It is not tree will not be constructed based on the traversals that you give. It is the other way around. Traversals are written. What is traversal? Visiting all the elements of a list of a data structure. If it is a list, then there is no confusion. Starting to end, you are going to write down all the elements. Since it is not a linear data structure, there is a mechanism like in order or pre-order or post-order. Any one of these techniques we use to make sure we are visiting all the elements. That's it. So it is only after a tree is existing. Okay. So now to implement binary tree, we have to be more specific. So there are different types of binary trees, and we will be writing programs for each of these types. Okay, so there are different types of binary trees. We are going to learn one by one. So the first one is you will have binary search tree. In binary search tree, the elements at the left of any given node are lesser than the elements at the parent node, or in other words, so if I have 40 here, all the elements over here are left less than 40, all the elements to the right of this node are greater than 40. So this is not just for the root element, for every element, that is for every node you are going to use this rule. So all the elements towards the left subtree of any given node contains data that is lesser than the node, and all the elements towards the right side are going to be greater than the elements in the parent node. So this is called as binary search tree. So suppose here I have 30, then here elements will be less than 30 and this side elements will be greater than 30, but remember this entire left subtree elements should be less than 40. Okay, so this is binary search tree. Here all the elements are going to be greater than 40. Suppose I put 80 here, the elements towards the left are going to be greater than 40 and less than 80, and all the elements towards the right are going to be greater than 80. So when I say the element is greater than 80, it is not just for this element. The entire subtree, say for example here greater than 40 I have written, this entire subtree elements are going to be greater than 40. Okay, it is for entire left subtree and right subtree, not just for the left, immediate left and right nodes. So this is called as binary search tree, where for any given element towards its left subtree all the elements are lesser, towards the right subtree all the elements are greater. So that is one type of tree. Next is height balanced trees. In height balanced trees, the elements are inserted not based on the content. Instead, they are going to be inserted based on the height of the tree. So if the tree is empty, first element will be inserted in the root. The next element which is inserted, without any question, it's going to be to the left child, and that next element is going to be the right child. So if you are inserting a fourth element, that is going to be the left of the left child. Okay, so it is going to be inserting in the every level, at every level it's going to finish the elements, and thereby it is going to have a consistent data structure, height balanced data structure. In that we further have AVL trees. AVL trees are height balanced binary search trees. Okay, so this is height balanced as well as they are binary search trees. Means binary search tree is where left side elements are lesser than the root element, right side elements are greater than the root element. We don't consider height there. In height balanced tree, we are going to insert the elements in the order in which we are going to give it as input, and we are not going to consider what is the data that I am inserting. Instead, whatever is the numbers, it's going to be inserted one by one, level by level. Therefore, height is balanced. And AVL tree is the one which takes into consideration both these options. And we have red black trees, AA trees, different types of splay trees, and there are lots of other trees. We will be seeing it one by one. But when it comes to implementation of binary tree as a program, we cannot just like that write a program for binary tree. It has to be a specific type of binary tree. Is it a binary search tree, or is it a height balanced tree, or is it a AVL tree? Based on all that, we are going to consider how to construct a tree. But once a tree is constructed, then we have to traverse the tree, right? So to traverse the tree, that is to visit the tree, we have three traversals: in order, pre-order and post-order traversals. So in today's class, we are going to see representation of a binary tree using array and also using linked list, how to do it. And as I told in yesterday's class, array implementation, I'm going to just tell you the concept. We are not going to write program for that, because it leads to lot of memory wastage. Other than if in case you are creating height balanced trees, then arrays is a good option. Memory wastage is minimum. But if you are creating a normal binary search tree, or based on input value, if you are creating a tree, then arrays is not suggested. Okay, so but all the programs that you are going to have in your universities or in the exams, if they ask, they're going to ask based on pointers only. Okay, they're going to ask based on this dynamic memory allocation, which is very much effective. They are not going to rely on arrays for such type of data structure implementation, because again, see, this type of data structures, they are going to use when there is huge amount of records to be stored, like say a hospital management system, they have thousands of patients records, hundreds of doctors records. And if it's a student management system, the number of students are going to be even more than the number of patients in a hospital, isn't it? So you will have lots of data, student data, college data, and teachers data. All these things needs to be maintained, and none all those things, no, it is not going to be just one integer int data like what we use in our programs. They're all going to be records. A complete record of one student needs to be maintained, which includes so many information. So for such things, we will make use of trees. List is not efficient there. We will make use of trees for implementing. There we might either give binary search tree or height balanced tree, depends on the data operations, frequent data operations, and also based on the preference and ease of implementation that is individual to each organization or the type of application that you are developing. Anyways, so now each of these types we will see in the next class. So in today's class, what we are going to learn is how to implement a tree, binary tree using array, and how to implement it using linked list. Not complete programs, but the concept. And array, as I told you, we are not going to do the traversals. But if it is linked list program, how to do all the three: in order, pre-order and post-order traversals. If you remember, for our linked list program, the first function that we wrote was for display, right? We wrote the display function. After that only we wrote the functions for each and everything, like insert, delete and all that. And after every operation, we just checked display function to make sure whether the code is working properly or not. All that insert code, whether it was working properly or not, we checked based on the output given by the display function. So here we are not going to have display function, because for displaying we have three different options: in order, pre-order and post-order. In which order you have to display, accordingly you're going to call that function. Okay, so next we will come to implementation of a binary tree. So as I told you, implementation of a binary tree is where we have both static implementation and dynamic implementation. So what is static implementation? We will be using arrays to implement a tree. So that is static implementation. Now, how do I use an array? So if you have to store values, then we are going to consider, or we will assign, theoretically we are going to assign position numbers for all the nodes. Let us consider an example tree, and then we will see how to implement that using an array. So I am going to write an example tree. This is BC. Then I'll have D, E, F, G. And here also I am supposed to have two elements, right? but for this particular this level, I will not write elements for all of them. I will write here H, and here I'll write I. Okay, no more elements. So here basically I don't have anything, blank. These are blank. Now for array implementation, we are going to first assign numbers, okay, numbers for each and every element, starting with root node as 1. So this is element number 1, this is 2 and 3. We are going to assign it level wise, okay. First level we have put 1, this is level 0, okay, which is 1, and then 2 and 3. So here I'll write 4, 5, 6, 7, 8, 9, 10, 11, and this is 12, 13, 14, 15. Okay, so I have assigned number values, that is numeric values for each of the node. Now after assigning numeric values, just do a little observation here. For every element, its child nodes are present in position number. So multiply this 1 with 2 and then plus 1. So that is the positions in which the numbers are present. So again I am reminding you, the numbers that I have written here 1, 2, 3, 4, 5, 6, it is only theoretical numbers. I am writing it so that I am going to make a plan for how to store it in system using arrays. Okay, so this 1, 2, 3 is not something which is existing in the system. This is something that is I am planning. Now for node number 2, where are the child nodes? 4 and 5. For node number 3, child nodes are at 6 and 7. So if the node number is n, then the left child is at node number for the left child is 2n, and for the right child node number is 2n plus 1, if you observe here. Understood? See, for node number 3, the left child is at number 6 and 7. See, for node number 7, left child is at 14 and 15. So based on this, we are going to insert the elements. So if I have to represent this particular data structure using an array, then this is how the implementation is going to be. So let me write an array with 15 positions. So this is 0, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15. This is number 2. Okay, so I'm going to write 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14 and 15. See, this is array implementation, therefore always the index numbering starts from 0. For an array implementation, you will always keep this first node empty. This is empty because if you store first node here, you cannot use this rule. Okay, so if you write there as 0, then 0 into anything is 0, so you have to start numbering only from the second element, and it is going to be 2n plus 1 and 2n plus 2. So that's how you will have to consider. Instead of that, this is preferred. Okay, this is standard preference. Therefore, for tree implementation, keep node number 0 or element at index 0 as empty or blank, or don't consider it. All your programs, you're not going to write from I equals to 0, it's going to be from I equals to 1. Okay, so I will store these numbers here. A is stored at number 1, this is B and C, then you will have D, E, F and G. So the left and right children of D is supposed to be at position number 8 and 9. And here I'm going to keep it blank because D doesn't have left and right nodes, and E also doesn't have left and right nodes, so position number 10 and 11 is also kept blank. F's left child is H, which is at position number 12, so here I'm going to write H. Then right child of G is I, so here I will write I. So this, if you observe, is the major disadvantage of arrays. We don't have continuity. Okay, so the continuity, establishing continuity is different, and for any node, its immediate nodes needs to be connected, right? And that becomes difficult to establish here. See, for E, elements are at 10 and 11. So it is a little difficult. For insertion it is at least okay, but if you have to delete some numbers or if you want to rearrange certain numbers, it becomes very complicated. Therefore, we are not going to use static implementation for trees. Okay, implementing, this is how it is done. If you have to write in order, pre-order and post-order traversals also, this is how it will be done. Because after writing a parent nodes element, if you want to write the left nodes element, you know where is the left node, right? So if the node is at array I, then left node will be at array 2 star I. Simple. Okay, and the right node will be at array 2 star I plus 1. So these are the things. So it is not that easy to you have too many to and fro's you will have to execute in order to write in order, pre-order, traversals and all that. Traversals are going to be easy, but inserting elements or removing elements, modifying anything becomes extremely difficult. And also this is a very balanced tree, right? See, all the elements are there. Only in the last level we had some missing elements. Otherwise, what if you don't have E here? Then there will be lot of missing elements, there will be lot of blank elements here. Therefore we don't prefer static implementation for implementing binary trees. But if you but this is very easy to write the program. But if you want binary trees to implement using arrays, then this is how it needs to be done. Okay, so this is about static implementation. Next we will see how to do dynamic implementation. Here for dynamic implementation also, let me take one simple example and show you how it will be executed, how it will be stored. Suppose I have a tree like this. Okay, so this is one example binary tree that I have taken. How dynamic implementation is done is, you know that for every element to be inserted, we freshly create a memory block, right? Here the memory block is going to contain 3 fields. One is a data field, one is a pointer field for having address of the left child, and one is a pointer field for having address of the right child. So let me assume I'm storing A here, and the left and right are going to be null initially. Let me assume this is at location number 500. Okay, now at left I need B, right? So let me assume B is allotted here somewhere, and this memory block is at location 600, suppose. Then here you will have 600. Okay, and to the left child C there is nothing, so it is going to be null. For right side C is supposed to be present. No, let's assume that is assigned here as 720 or something, which is C. Okay, so that will be stored here. Now for C there is no left and right child, therefore it's going to be null. Next I will have D. For D, I will write left child at 800 and right child at 400. Okay, so at 800 there is some memory allotted for this. So this is location 800. Here the value that I am storing is E, and then this is null, and this is also null. I am going to have one more number here, memory block, which says memory location as some 900. I'll take. This is F. This also doesn't have any left elements and right elements, right? So this is how internally, that in memory, this is how it will be stored. So the first node is at root, and root is a pointer which has address of this node. Okay, so root is a pointer variable, and there I am storing 500. So at 500 whatever is there, that is my root element. Then this has D is here, no, which is say I will take location number as 1000 for this, so it's stored at 1000. Okay, so for node A, the left child is at address number 600, right child is at address number 1000. Okay, which is D. Left child 600 is here, which is B, which doesn't have any left nodes, therefore null is present. Right node we have at number 720, which is here. Okay, so which doesn't have left and right pointers, both are assigned to null, means it is an empty leaf node. Now let us see how to implement this using a code. So we have to write a structure. This we have already done for linked list. So I'll name this as node. We need to store one data element. Okay, and then we need to have two pointers here. One is the left pointer, one is the right pointer. So I will create struct node star left comma star right. So this is how we write the structure. Now we have traversals. Okay, so for traversals we have in order, pre-order and post-order traversals. For all these we are going to write recursive definitions. We can write non-recursive definitions also. I will write a program. I will give you a program. I'll share it in the WhatsApp and Telegram channels. If you have not yet joined, then you can go to the link below and join the channels. If you are already part of any of the WhatsApp group, then you don't have to join the group that is mentioned in the description, because all the groups are full. This is a new group that is created. Whatever data is shared will be shared with all the groups simultaneously. Same content will be shared. So if you are already part of any of our WhatsApp group, then there is no need to join this programming group. We have what's aptitude group also, programming group also. If you are part of either SRM group or programming group, then you don't have to select the link present in the description. If not, make sure you're going to join that WhatsApp group and also the Telegram channel to get all these programs. Okay, now for pre-order, in order and post order, we have non-recursive traversals, for which I will share the program. But right now we are going to write the recursive definition, which is very easy. So we are going to have a node pointer as the parameter. So what is pre-order? We need to display parents element first, then we go to the left child, then we display the right child. And in left subtree, again we are going to follow the same procedure, right? We will display parent element, then we'll go to the left and right. So whatever this PLR rule is there is to be applied for each and every node. Therefore, void pre-order. So what is that I am supposed to do? First, print element present in the root. Okay, you can even take it as temp, anything is fine. So you can take it as temp, whatever, because that is the parameter over here. Whatever parameter is passed, you will print off data over there. Then you will have to print the left element, then go to the right element. And left element not just printing, that should further be treated as a tree only, because it is a subtree as well. So we are going to call the same function pre-order by passing the address of the left pointer. Okay, root left, pre-order root right. So we have to print an element at the given pointer, and then we have to traverse to the left child, and then we have to traverse to the right subtree. And this is to be done only if the node is not null. If the node is null, means it's not existing, there is nothing to print, and definitely there is no left and right child. So this you will be doing only if the parameter that we are considering is not equal to null. Understood? So the root node that we are considering is not null. If it is not null, then print the element and go traverse the left subtree and right subtree also. If it is null, then we just return to the previous function. Okay, previous function call, because this is recursive function call. Now here we are going to have the recursive definition of all the three traversals. So it's extremely easy to write recursive definition for this particular program. So this is pre-order. For post order, everything is going to be same. Instead, in place of pre, you are going to write post. And in the code, we are going to write, if root not equals to null, root data, printing data should be the middle instruction for in order. root. So what is in order or arrangement? This is pre. For in order, it is left parent right. Okay, left child, parent, right child. So first we display, we traverse left subtree by giving in order root left. Then we traverse right subtree giving in order root right. Okay, then in between these two instructions you are going to write one printf statement, and in that printf statement we are going to print the value of the data before proceeding to the right subtree. After printing elements of left subtree, before proceeding to the right subtree, we can have one printf statement. Okay, so this is traversals using pre-order. We also have in order and post order traversals. Okay, now let me write program for the same. As I told you, we will not be executing it today because so here I will write implementation of binary tree. We will include stdio.h header file. If required, we will include other header files. As of now, it's not required. Okay. After including the header file, we are going to first define the structure. There are no global parameters, so I'll first define the structure. Struct node. I will write int data. Struct node star left, star right. In the previous programs, I've told you I don't want to type struct node every time, so I'm going to give a different name for this, and to give an alternate name we need to use type def instruction. So I have told you the procedure, no, to write lengthy programs, what all things you need to decide before you start writing the program. I have told you, first you decide what all functionalities to be used. Okay, so what all functions you require, that you write down. Then decide on the prototypes of these functions, means for each function what all parameters you need and what parameter it should give back as the output. So these are the function prototypes that you have to decide. After deciding on function prototype, you start writing the logic of the program. So the first thing to decide is the representation of data. Here I have decided it is going to be that pointer implementation. Next we have to list out what all operations we want on this data to be performed. So the first one is insert operation, and then we have delete operation, and then display. So when it comes to display, we have different types of display. So we have pre-order, in order and post order traversals. Okay, so insert, delete, pre-order, in order and post order traversals. These are the things we are going to have. If required, we can have a search option also. For searching, basically we are going to search whether an element is present or not. That's going to be the output. To check whether element is present or not, you have to actually visit the entire nodes of the tree. For this, use any one of the traversal methods, pre-order, in order or post order. You can use any one of the traversal method. If it is present, we are going to mention that the element was present, element whatever you are searching for is present in the list. Or if you are not finding it, just display that the element is not found in the tree. But in the tree, you can, searching for an element, you can use any one of the traversing techniques for searching. Okay, these are the functionalities that we want for this program, and we have to now decide what all inputs and outputs will be required for this program. So for this, insert, as we have done in linked list programs, we need to return the pointer type as well. When I insert in the first position, or whether we insert in the left or in the right, we will have to return to the main calling function whatever is the address of the newly created node. So we need node star insert. I am going to mention the number to be inserted in case of a binary search tree. the element to be given is different. In case of a height balanced tree, the data that needs to be given is different. So let us write insert function later, or let me write it as based on binary search tree. I am writing the insert function. The logic for inserting and deleting in a binary search tree we will see in tomorrow's class. Node star insert, number to be inserted and the pointer where we need to attach this element, and the number that needs to be inserted. Okay, so this is going to be the function prototype for insert operation. For delete operation, I have to specify again the pointer and the number to be deleted. This should also return the pointer. So this is going to be the inputs required for insert and delete. For other things, you need the pre-order, in-order and post-order traversal. You just need the pointer. And for searching also, you want the pointer as well as the element to be searched. Okay, there also the prototype is going to be same. So now let me write the prototypes for all these 6 functionalities. So node star insert, here I am going to pass the pointer and the number to be stored. Next, for deleting, node star int, next is display. Display doesn't return any value, so I will give pre-order node star. Void post order node star in order node star, and we will have search functionalities. As of now, we don't have any thing to be returned in a search functionality, so that I am giving just void. So these are the functionalities that we have in our program. So next I'll write the main function. For the main function, I'm going to first create the root element and make it null. I need a number to be stored, and then I think I need choice. Okay. Now we have to write everything in a do while loop, so you already know this. Same procedure we are going to follow here as well. So we are going to first write binary tree implementation. Next we will write all the menu options one by one. One for insert an element, next is we have to write, after insert we will be writing delete, then we will look for in order display or in order traversal. The order in which you are going to give here doesn't matter actually. Next we have pre-order traversal, next is post order traversal. Next I'll write searching for a given element. Sixth option, search for a given element. Now the last option is exit, and this also I've told in the previous class. Based on number of functions you have, the number of options that you're going to write in this do while loop is one additional, because one option you give for each of those functionalities, and for exiting we are going to use one option. Now just we will write enter your choice. Scanf %d ampersand. So now we have the choice from the user. Now based on the choice entered by the user, we have to write the specific code. So if the user has asked to insert an element, then we are going to take the information accordingly. Therefore, we will write switch choice based on what the user has written. Case 1 is if the user wants to insert one element to the list. So printf enter number to be inserted. And we store this scanf %d ampersand num. We call insert function root equals to insert root comma num. Then we give a break statement. Next is we give enter the number to be deleted. Scanf root equals to delete root comma num. Break. So insertion and deletion operation is done. Next we have to go for in order traversal. Just call in order function, that's also the third option is in order traversal, right? So in order root, that's it. Next is case 4, which is pre-order traversal, which also requires the root node. Then you have break. Case 5, post order traversal and root. Is it name of the functions correct? In order, pre-order and post order I have to give in capital letters. Yes, we can make it actually more refined. Okay, so we can write if root equals to null, we will write empty tree. That's it. We are not going to display anything if the root is null. Else, so if the root is not null, then we are going to execute all this. In order traversal are as follows. Right, so break. This is what we are going to do for everything. This I'll copy paste for all the cases. Empty tree. Otherwise, pre-order traversal is as follows, and here I'll make it pre-order. Next is case 5. Here again we'll paste it. If root is null, empty tree. Otherwise, post order traversal is as follows, and here I'll give post. Okay. Case 6 is to search for an element. Whatever the user enters, store it in the number, and call search function. And this is not going to give back any element, therefore it is void. Okay, then we will write break. Case 7 is for exit. I'll just write one printf statement, end of binary tree. Implementation. If we enter some info which is not any of these, then we will display invalid input. Invalid input or invalid choice, whatever you want, you can mention. For the last statement, we don't need a break. While choice not equal to 7, because 7 is the option for exit. Okay. So this completes the main function. I'll save it using binary tree.c. So if you observe, as of now we have declared the structure definition. I have given function prototypes for all those things. Then we have main function where I have given like a menu, insert and delete option is present, and 3 types of traversals are present, and searching. Based on what choice the user enters, appropriate information is taken and we are displaying the content. And now we have to write the function definitions. Definition for each of these functions one by one we need to write. Hope as of now you have understood everything. So the remaining part will continue in tomorrow's class. So in tomorrow's class we are going to be including all the pre-order, in-order and post-order traversals and the insert and delete functions, assuming that it is going to be a binary search tree. If this whatever we have written so far, it is common for all trees, whether you have a binary search tree or height balanced tree or AVL tree. Today's content that I have written as a program, this is common for all the trees implementation, and only insert and delete inside that code is going to modify, and sometimes you might need one or two few small extra functions, but whatever is written in today's class, this entire thing, okay, this is the common code for all types of binary trees, binary search tree, height balanced tree, AVL tree, these 3 programs, it is common. So this common code I will share it with you all, so you can use this. Based on this you can write the other content for, specific content for each of the types of trees. Go through all these concepts clearly and make sure you go through all the videos that is done so far. In tomorrow's class we'll continue this program with respect to each and every type of the tree. Okay, fine. See you all in next class. Take care. Bye bye.